Um, Sorry for the interruption. So just continuing from the last video, doing question 3, Math 3274, assignment 3, and we have the following assumptions. We assume P of 0, and we assume that P of n implies P of n plus 1 for all n less than k. We have to show P of n for all n less than or equal to k. Okay, so notice we can't just directly apply induction, because to apply induction, we need this to hold true for all natural numbers n. And this only holds for all the natural numbers less than k. But luckily we don't need the full strength of like if that were true for all natural numbers n, we would conclude P of n for all n, natural numbers n. But we don't need that, we need this like weaker statement. So we have a weaker assumption and a weaker statement. Maybe there's like some hope to prove this. And it's just like kind of a tricky proof, I guess. Okay, we just define a new property. Q of n is going to be the property that either P of n or n is bigger than or equal, or let's say n is bigger than k. Okay, so it's just like logically it's P of n or n is bigger than k. So if P of n holds, then Q of n holds, and if n is bigger than k, then Q of n also holds. Okay. And we're going to prove Q of n by induction. Okay, so we're going to apply induction for Q of n. So Q of 0 holds, since P of 0 holds, okay, assume n is a natural number, and assume Q of n. Okay. So there's two cases, either P of n or n is bigger than k. So, case 1, n is bigger than k. Well, if n is bigger than k, then n plus 1 is also bigger than k. So Q of n plus 1. Because we only need one or this or this for Q of n, like Q of n plus 1 just says P of n plus 1 or n plus 1 bigger than k. We've shown n plus 1 is bigger than k, so Q of n plus 1. The other case is that P of n holds. P of n. Okay, in this case, there's two possibilities. Okay, so we know that either n is bigger than k, n equals k, or n is less than k. So we have like subcases. Subcase 1 is that n is less than k. If n is less than k, and we know that P of n, then we know that P of n plus 1, since n is less than k. By hypothesis, not induction hypothesis, just that is what's given to us in our assumptions for the question. Okay, and there's one thing left to do, and that's we have to, what if n equals k? Subcase 2, n equals k. Well, then n plus 1 is just k plus 1, which is bigger than k. Okay, so that implies Q of n plus 1, and P of n plus 1 implies Q of n plus 1. So in either case, we have Q of n plus 1. Okay, so now we can, finish off. Sorry, that is the end of number 3 almost. So we just finish things off. So in either case, Q of n plus 1. So we've shown that q of 0, and we've shown q of n implies q of n plus 1 for all n. So therefore, q of n for all n by mathematical induction so therefore either p of n or n is bigger than k, n is bigger for all n. Okay, in particular, if n is less than or equal to k, then we have p of n. So for all n is less than or equal to k, we don't have n is greater than k, so we must have p of n. Okay, and that's the end of number 3. And number 4 is just like a tricky induction proof, which, is fine. Okay, so we just write down our statement. Okay, so let me remind you, we're supposed to prove that the summation from k equals 1 to 2 to the n of 1 over k is greater than or equal to 1 plus n over 2. We're supposed to prove this for all natural numbers n. Okay, so solution, well, let's just call this inequality, we'll call it p of n. Call it p of n. Okay, p of 0 is just a statement that the summation from 1 to 2 to the 0, in other words, the summation from 1 to 1 of 1 over k, which is just 1, just says 1 is bigger than or equal to 1 plus 0. Of course, that's true. That just says 1 is bigger than or equal to 1. Okay, now we assume p of n. That is, we just assume summation from k equals 1 to 2 to the n of 1 over k is bigger than or equal to 1 plus n over 2. We have to prove p of n plus 1. Okay, so first we write summation from k equals 1 to 2 to the n plus 1 of 1 over k. Well, we just rewrite it as a summation, like we divide these terms in half. 1/2 comes from this sum, so let's write that. And the other half comes from the summation from 2 to the n plus 1 to, 2 to the n plus 1 to up to 2 to the n plus 1. Okay. By mathematical induction, this is bigger than or equal to 1 plus n over 2. Oops. Okay. Now we have a sum of a bunch of positive numbers, and they're all decreasing. The least one is when k is largest. Okay. So let's see, I have to continue this. So I'll continue this inequality on the next line. So greater than or equal to 1 plus n over 2 plus summation from k equals 2 to the n plus 1, 2 to the n plus 1. And instead of 1 over k, I'll just replace it by the smallest it could possibly be in this range, which is 1 over 2 to the n plus 1. And I have 2 to the n terms, each this big. So I have 2 to the n over 2 to the n plus 1. In other words, a half. That's 1 plus n plus 1 over 2, the end. Oh yeah, I guess that's not the end because, you have to, that's just the, we did base case, induction hypothesis, induction step, that's the end of the induction step. So we've shown p of n plus 1, and then, we just have to write our conclusion and all that stuff. Okay, so therefore p of n plus 1 holds by induction. Here's our conclusion. For all n, p of n, which just means for all n, summation from k from 1 to 2 to the n of 1 over k is greater than or equal to 1 plus n over 2. And that's the end of the inequality. And I like this inequality. It tells you just by like using induction, you can, and just basic arithmetic, you can show like this the harmonic series diverges and like kind of how fast it diverges, I guess. Okay. So that's the end of the solutions for assignment 3. Okay, thank you.